Let's finish our discussion on limits by finding limits as x goes to infinity. We're going to do the same thing we did before. To start, we're going to do the same thing we did before. To start, I am actually just going to plug infinity in for x. I have infinities on the top and infinities on the bottom. That is starting to look indeterminate to me. I don't really know what's happening here. And so the work that I'm going to do in these problems is I'm going to take the function and just divide every term by the largest power of x. In this particular case, that means I'm going to be dividing everything by x squared. So I divide both the 2x squared and the 1 by x squared. And then I divide everything in the denominator by x squared. And if I simplify this, in the numerator, I'm just left with a 2 plus 1 over x squared. And in the denominator, I have a 3 minus, and then one of the x's cancels out, so 5 over x, plus 6 over x squared. And now I'm going to plug my infinity in again and see what happens. So I plug infinity in for all of those x's. And anytime you have a constant divided by infinity, like 1 divided by infinity, or even infinity squared, that's still infinity, a constant divided by infinity always goes to 0. So this 1 over infinity, 5 over infinity, 6 over infinity, all of those terms go to 0, and all I'm left with is 2/3. And that's my solution, y equals 2/3. My limit is equal to 2/3. This is the same thing as finding a horizontal asymptote. So if you have learned other methods of finding horizontal asymptotes in the past, hopefully this answer matches y equals 2/3. All right, let's do a couple other examples that are similar. This process works for negative infinity as well. I'm going to go through and I'm going to divide everything by that largest power of x. In this case, it's x squared. So I divide the numerator by x squared, and then I divide both terms in the denominator by x squared. And if I simplify everything, I have a 6 over x in the numerator and a 1 plus 4 over x squared in the denominator. Once again, I'm going to plug in my infinities now. So I've got 6 over infinity plus 1, or over 1 plus 4 over infinity squared, which is still infinity. Anytime I have a constant over infinity, that goes to 0. And so in this problem, I'm left with 0 over 1 plus 0, which is just 0. It's okay to get an answer of 0. What's not okay is you can't get that indeterminate 0 over 0. All right, let's do one more that's similar. I'm going to divide everything by my largest power of x, which in this case is x cubed. So everything in the numerator gets divided by x cubed, and everything in the denominator. Then I'm going to simplify. In the numerator, I'm left with 1 minus 3 over x squared. I just canceled an x out of that second term. And in the denominator, I have a 1 over x squared plus 7 over x cubed. Once again, I plug in my infinities. 1 minus 3 over infinity. And if you don't want to write down the squared, that's okay. Infinity squared is still infinity. And then I have a 1 over infinity plus 7 over infinity. Anytime I have a constant over infinity, that goes to 0. And this time I'm left with 1 divided by 0. This is still not indeterminate. It's only 0 divided by 0 that is indeterminate. This information tells me that this particular limit is undefined. What this means is that as x gets really large, the y values get really large. Or this would be the case where you actually have no horizontal asymptotes. I'm just going to write undefined for that limit. Finally, I'd like to finish up by doing an application problem. So this problem says it has been determined that the depth of sediment, D, so D is depth of sediment, with respect to time in years before 1990 for Lake Coeur d'Alene can be estimated by the equation. Find D of 20. So find d of 20 simply means plug 20 in for t and see what you get. So I'm going to replace the t with a 20, and then I'm going to have to use a calculator to help me finish this problem. So I just put this into my calculator. This is Desmos, which is the online calculator that I like to use. So it looks like I got about 36 or 36.2. So d of 20 equals 36.2. Now we're asked to interpret, and so let's see, t is years before 1990. So if t is 20, that means it must be 1970. 20 years before 1990. And d is the depth of the sediment in centimeters. So we could say in 1970, the depth of the sediment in the lake was 36.2 centimeters. Now the second part of this problem is asking us to find a limit. It's asking us to find the limit as t goes to infinity of that exact same function. Okay, so I'm going to try to find the limit as t goes to infinity of 155 times 1 minus e to the negative 0.0133t. So my advice when you're finding limits and you have negative exponents is to rewrite them as positive exponents. So we can actually rewrite this as 155 times 1 minus 1 over e to the 0.0133t. So negative exponents mean reciprocals. You can take something with a negative exponent and just move it to the bottom of the fraction to make the exponent positive. Then I'm going to plug my infinity in. And 0.0133 times infinity, anytime you multiply a number times infinity, you still get infinity. So this is 155 times 1 minus 1 over e to the infinity. And well, e to the infinity is actually infinity as well. So I'm going to erase that and change that. And now we can use that rule that anytime we have a constant over infinity, it always goes to 0. And so we are just left with 155. This limit is equal to 155. Okay, well, what does this mean? As t goes to infinity, we're talking about an infinite number of years before 1990. So I guess we could say a very long time ago, or when this lake first formed, we had 155 centimeters of sediment. So I'm going to write when, So I'm going to write when the lake first formed, there was 155 centimeters of sediment. That amount has declined quite a bit. Again, it would be perfectly appropriate to just say a long time ago or many years before 1990 in your interpretation. So I hope this helps. I know there's a lot of information in this section, so please don't hesitate to ask if you have any questions.